Time for the ideal gas law, PivNert. We get this equation from combining the other gas laws. Okay, remember, with Boyle's law, pressure times volume equaled some constant. Pressure over, or volume over temperature equal to constant. And volume over the number of moles equal to constant. Well, that constant, when we combine all the constants, turns out to be something we call the ideal gas constant, capital R. And so really the ideal gas law is PV over NT equals R. But we don't like fractions. So we just multiplied both sides by N and T and stuck the R in between them so we could pronounce it as PivNert. For this, we are always going to use R as 0.08206 liter atmospheres per mole Kelvin. That means we're always using the units of liters, atmospheres, moles, and Kelvin. If we use any other units for pressure, R is going to be a different number. If we use any other volume than liters, R is a different number. If we use temperature in degrees Celsius, which is stupid, we always use Kelvin, we have to use an absolute scale, R would be a different number. For now, we are always going to use PivNert in liters, atmospheres, moles, and Kelvin. I have had college professors who required us to memorize R in different units. For the AP, we only need to know that R is 0.08206 liter atmospheres per mole Kelvin. You can change any other pressure to atmospheres. You can change any volume to liters. You can calculate moles. You can change temperature to Kelvin. So we don't have to memorize anything else. You just change everything over into those 4 units, and you're all set with this one. And really it's a matter of plugging numbers in, solving for the unknown. So for this sample problem, we have calcium carbonate decomposing, and you should know that when a carbonate decomposes, it releases carbon dioxide and leaves behind a metal oxide. They collect the carbon dioxide in a 250 milliliter flask, and we assume that there was nothing else in the flask. It was a complete vacuum in there beforehand. So the pressure in the flask now is 1.3 atmospheres in a 250 milliliter flask, and the temperature is 31 degrees Celsius. How many moles of carbon dioxide were generated? Well, we just put in this information. Put in 1.3 for the pressure, put in a quarter of a liter, 0.250 liters. So and for the volume, we multiply those two things. So 1.3 times 0.250 gives us 0.325 liter atmospheres on the left. On the right, we can take our R, 0.08206, multiply it by the temperature in Kelvin. Now, Kelvin, we have to add 273, so that makes it 304 Kelvin. So 0.08206 times 304 gives us 24.95-ish, liter atmospheres per mole. Then we just divide. The pressure volume divided by the RT is going to give us our number of moles. And I'm figuring that out right quick here. And I get 0.013 moles. Very small amount of moles, but that's a very small volume. And remember, gases spread out very well. So check your calculation, see if you can come up with the same thing I got, 0.013 moles of CO2. Now we can take the ideal gas law and relate it back to the other gas laws that we've looked at. Boyle's law, pressure times volume is a constant. And if we change the pressure, the volume will also change. And if we keep the temperature the same, that constant's the same. So pressure 1 times volume 1 is a constant. Pressure 2 times volume 2 is a constant. Well, those two constants are the same. And if you think back to geometry, if A equals B and C equals B, A equals C. So in this case, if P1V1 equals a constant, P2V2 is a constant, P1V1 equals P2V2. Same with Charles' law. We can do the exact same process, and we end up with V1 over T1 equals V2 over T2. Gay-Lussac is another French, and it is pronounced Guy, who looked at pressure and temperature relationships and found, not surprisingly, you increase the temperature, you increase the pressure. It's directly related. So P1 over T1 equals P2 over T2. If we combine those three, we get what chemists call, unsurprisingly, the combined gas law. P1 V1 over T1 equals P2 V2 over T2. We use the combined gas law anytime pressure, volume, or temperature are changing of a sample. If there's no change in the sample, if we're just missing a piece of information, we use the ideal gas law, the Pivnert. So if I give you three of the four pieces of information, pressure, volume, moles, or temperature, you use Pivnert to find the missing one. If I say we have a sample of gas and something is changing, pressure's changing, volume's changing, temperature's changing, we use the combined gas law because it's got the ones and the twos. Now anything that's not changing we can just ignore. If I say we've got, the sample of gas and it's kept at constant pressure, the volume changes, what's the new temperature, we can ignore pressure and just do V1 over T1, V2 over T2. It becomes a Charles law problem. So only memorize Pivnert and the combined gas law, and then just ignore whatever thing's constant in the combined gas law. So let's take a look at this sample problem. Gas pressure in an aerosol can is 1.5 atmospheres at 25 degrees Celsius. Celsius, change to Kelvin. Good. Assuming the gas inside obeys the ideal gas equation, what would be the pressure if the can were heated to 450 Celsius? Change to Kelvin. All right. Is something changing? Yes. The temperature is changing. So we're going to use the combined gas law. What thing is holding steady? Well, we've got an aerosol can. That's like a hairspray can. That's got stiff sides. It's not going to swell up or shrink down. The volume is constant. So we can ignore the volume in the combined gas law. So we just have P1 over T1 equals P2 over T2. This is Gay-Lussac's law. Put in the numbers, make sure you use Kelvin, solve for the missing pressure. All right, we have another sample problem here. Let's see which law we're going to use. An inflated balloon has a volume of 6 liters at sea level, which is 1 atmosphere, and is allowed to ascend until the pressure is 0.45 atmospheres. We have something changing. We're going to use the combined gas law. During ascent, the temperature falls from 22 to 21 degrees Celsius. Okay, first we need to change those to Kelvin. Calculate the volume of the balloon at its final altitude. All three things are changing. Pressure is changing, temperature is changing, volume is changing. We can't ignore anything. So we'll put in P1 V1 over T1, and we use sea level for those. So P1 at sea level is 1 atmosphere, V1 is 6 liters, T1 is 22 degrees Celsius, whatever that is in Kelvin, equals P2, that's at height, so that's 0.45 atmospheres. V2 is our unknown. We can put X in there, or V2, or however you want to write it, over T2, 21 degrees Celsius. Solve for that missing piece. In class, if you're having trouble manipulating these 6 variables like this, in class, I'll show you some hints on how to do that. I call it collapsing both sides and then solving. We'll talk about that in class if you're having problems with this. But this is nothing more than an Algebra 1 solve for the missing piece type problem.